Okay, in section 4.2, we're going to look at null spaces, column spaces, and transformations and how they relate to vector spaces. So we've talked about all these things before, talked about them in chapters 1 and 2. We're going to now look at them through the lens of a vector space, okay? And so a lot of 4.2 is very repetitive of what we've done before, okay? We repeat a lot of the things. We've just kind of looking at them through a slightly different lens, okay? So the first thing to know is that a null space and a column space are each vector spaces. So the null space and column space are both vector spaces. Okay, and let's think about why that is. So in order to be a vector space, right, we have to meet those 10 criteria, okay? Well, if I'm in the column space, then I am the linear combinations of all of the columns of a matrix A. So if I think about the linear combinations, remember we said that a span or a spanning set generates the linear combinations, which gives us those 3 criteria for being a subspace. Closed under vector addition, closed under scalar multiplication, okay, not just multiplication, but scalar multiplication, and also that the 0 vector is in there. So the 0 vector is in the column space because we always have the trivial solution, okay? Now the 0 vector is also clearly in the null space because A times 0 is going to be 0. Vectors in the null space are such that when you multiply them, you stay at 0. So if I have 2 vectors, so if x and y are both in null A, then ax is equal to 0, as well as ay is equal to 0. Well, if I take x plus y, I know that a times that is going to be equal to ax plus ay, which is 0 plus 0, which is 0. Okay, so it clearly passes the test here for vector addition. And now if I do scalar multiplication, remember that I can bring the scalar out to the front. I have associativity with scalars, so I get c times 0, which is 0. Okay, so clearly the null space is going to meet all the criteria to be a vector space, the same as the column space. Okay. Also remember that the null space and the column space are subsets of particular Rn or Rm, depending on which one they are, the null space or the column space. Okay, so let's look at a quick example here. So if I have 1, 0, 2, 1, 4, 3, and 0, negative 2. Okay, this is my matrix A. So if I look at my matrix A there, I know that if I was doing A times X, right, A times X, I would have to multiply by a 4-component matrix, right, x1 through 4, because I have to have the same number of entries in the matrix that I do columns in, same number of entries in the vector that I do columns in the matrix, so 4 each place. Okay, so given I have 4 each place, those have to line up. And when I multiply this, my product here is going to just have 2 components to it. Okay, so looking at the vectors here that are in the columns each have 2 components. So the column space of A is going to be contained in, or a subset of, R2, where the null space of A is going to correspond to these vectors I'm multiplying by to get 0. Remember, to be the null space, I would have AX equals 0. The null space is going to be contained in R4, okay, because I have 4 columns going across there, okay? Now, I also want to figure out things like what's linear independent, okay? What is the spanning set? So if I take a look at A here, and we're going to row reduce A, okay? So type in your matrix here, 2 by 4, 1, 2, 4, 0, 0, 1, 3, and negative 2. Okay, do your row reduction, and I'm going to get 1, 0, negative 2, 4, and 0, 1, 3, negative 2. Now, since those vectors were in R2, we knew we could only have at most 2 of them be independent. Okay, so take your columns from A. So the column space of A is equal to the span of those first 2 columns, 1, 0, and 2, 1. Remember to get them from A originally, not from the reduced matrix. Okay. Now I can pretend that this is augmented with zeros here, so I would have a solution set would be x1 is equal to 2x3 minus 4x4. So remember, I'm moving those to the other side of the equal sign. x2 would be equal to negative 3x3 and plus 2x4, while x3 and x4 would be free. Nice, we'll just say they're equal to x3 and x4. So my null space then, I have an x3 vector. Okay, I have 2, negative 3, 1, and 0. Again, just writing the coefficients of x3 going down here. x4, okay, I have negative 4, 2, 0, and 1. Okay, so the null space of A then is the span of those two vectors. That gives us our spanning set for the null space. Okay. This also tells us, since this is the span of two vectors, that it's a subspace. So these are both subspaces. Okay. All right. So we call this an explicit description of the null space, either this or this. Okay. Pay attention to what it asks for. If it's asking you for a vector representation, you get vector representations. Asking for equations, you can get equations. Either one. Okay. Now we want to relate this to what we've been talking about with vector spaces, what we talked about in section 4.1. So let's consider a space W. Okay, this space W is a subset of R4. So it has A, B, C, and D. Okay, and the conditions on A, B, C, and D here, I have 2A is equal to 3B minus C. And I have B is equal to negative D plus 3C. Okay, so I have those two conditions. Okay, ultimately, this is a set of linear equations. I can write that set of linear equations as a homogeneous system. So I have 2A minus 3B plus C equals 0. And I have B plus D minus 3C equals 0. Now be careful here, because my components here are written out of order. And I go ABC, but this goes BDC. So if I go to write a matrix representation of this, make sure you keep them in the same order. So this first equation would be 2, 3, 1, and 0 for D. This 0 is not the 0 vector that's augmented. Okay, this 0 is that I have no D components for that one. Okay, second equation, I have no A's, 1B, negative 3C, and 1D. And again, no component. It's equal 0 for a homogeneous equation. Okay, so I have a vector space here. Okay, I can write the column space and the null space of this vector space, which I know are subspaces, by taking my matrix, which is a 2 by 4, punching it in, and then I want to row reduce that matrix. Okay, when I row reduce this matrix, I get the following. I get 1, 0, 5, and negative 1.5. Again, augmented with 0. And 0, 1, negative 3, and 1. Again, augmented with 0. So I can write the column space then as the first two columns. Okay, so the column space of W would be equal to the span of 2, 0, and 3, 1. Okay, those first two columns, because those are the independent columns. Okay, and then I'm going to write the system of equations over here. I'm going to have x1 is equal to negative 5x3 plus 1.5x4. I'm going to have x2 is equal to 3x3 minus x4. x3 and x4 are free. Okay, so I can use that to write the null space of W is the span of what two vectors here. Okay, so for x3, I have 5, 3, and 1. Sorry, negative 5, 3, 1, and 0. And then for my second, I have 1.5, and negative 1, 0, and 1. So 1.5, negative 1, 0, and 1. So if I needed a vector in the null space, I could pick any linear combination of these two vectors. If I needed a vector in the column space, I could pick any linear combination of these two vectors. Although, since they're in R2 and there's only two of them, I actually cover the whole space, right? The span of this is actually equal to all of R2 because I have 2 dimensions and I have 2 basis vectors, okay? So 2 components, 2 basis vectors means I get the whole space. Notice I do not get all of R4 here because I only have 2 vectors, okay? But notice that they are inside of T, okay? Inside of W, I should say. All right, now we also want to relate this to linear transformations. So if I pretend this matrix here, this matrix is A, and I set up a linear transformation that's equal to AX, okay? I know this linear transformation is 1-to-1 because I have a pivot in every row, okay? It's not on, let me try that again. I know this linear transformation is onto because I have a pivot in every row. It's not 1-to-1 because I do not have a pivot in every column. I only have 2 pivots where I have 4 columns, right? If it's going to be 1-to-1, you should get that the null space is only the 0 vector. You have non-trivial solutions. You do not have a 1-to-1 transformation. The other thing to notice here is that this column space is all of the outputs. Okay, the column space is all the outputs if I multiply. When I multiply, look back up here, right? I did a 2x4, I got an R2 matrix out, right? This was a component of R2. It was contained within R2. So the column space is actually equivalent to the range of a transformation, okay? Column space is equivalent to the range, okay? The null space is equivalent to what we call the kernel, which is to say it's all the places where T of X is equal 0. That is the kernel. Okay, so kernel is just another word for null space. Okay, in certain contexts, you will see the two used totally interchangeably. Okay, the null space refers to vectors, the kernel refers to linear transformations. Okay, so the null space of a linear transformation is the kernel. Okay, now remember, not every space is a vector space. We can have things that go wrong. So let's look at another example of a W here. I'll say I have a vector space, or a possible vector space, I should say, W. That's equal to RST. Okay, and I have conditions here that R plus S is equal to 2, and minus R plus S is equal to T. Okay. Well, if I go to try to write the matrix for this, right, I'm going to have 1R, 1S, no T's. Okay, 1R, 1S, no T's, but then it's equal to 2 on the other side of that augment. Okay, I would have negative R, 1 copy of S, and then I would bring the T over. I get negative 1T, and that's equal to 0. Okay, but notice here that the 0 vector is not in W. Okay, the 0 vector is not an element of W. Why? Because if I put in 0 for R and S, R plus S will not equal 2. Okay, so the 0 vector is not in W, so this is not a vector space. Okay, so if it's not a vector space, I can't use it to define a null space or a column space. Okay, I don't have a linear transformation. Okay, it doesn't work. It's not consistent. Okay, so you have to be mindful of that situation where it won't line up in that fashion. Okay. So if you have a matrix A, even if you don't do any operations on it, so let's just take a random one here, 2, 1, negative 1, 2, negative 3, 1, 1, 0, 1, 2, negative 4, 3, 1. Okay. I have a matrix A. Okay. The null space of this A would be contained in R3 because I have 3 columns. The column space of A here would be contained in R4 because I have 4 rows. Okay, so the vectors in the column space, right, you would figure out which ones are independent. They're all independent. That tells you something about the null space. The null space, right, you solve if AX equals 0. Okay. Now, something to be mindful of is when you're looking for a vector that's in the space, okay, be careful. So let's take a matrix A here. This is going to be 3, -1, -12, 4, 6, -2, and 15, -5. Okay, and I'm going to row reduce this matrix. So this matrix now is 1 and -1/3 with all zeros here. Okay, when I row reduce that, that's what you should get. Okay, so for the null space, I know that x1 is equal to 1/3 x2, and x2 is free. Okay, so I can write the null space then, null A is going to equal to the span of the vector 1/3, 1. Okay, so that's an example. Remember, the zero vector is always in the null space. It's always in the column space as well. Okay, in the column space here, I only have one independent column. That's the first one. So that is 3, -12, 6, and 15. Okay, so if I'm going to find a vector in the column space, it better be a multiple of this vector. If I'm going to find a vector in the null space, it better be a multiple of that vector. Okay, now notice that all the examples I'd worked before kind of had the larger space being the null space. We had more columns than rows. Well, here I have more rows than columns, so you can't arrange those accordingly. You have to pay attention to which one is which for the given matrix. Okay. So another shot here, if I've got a matrix A that is -2, 10, 3, -15, and I have a vector B here. This vector B is -2, 3. Okay, so I want to figure out if that vector is in the column space or the null space. Maybe both, maybe neither. So is it in column A? Is it in null A? Is B an element of column A? Is B an element of null A? Okay. Well, to figure out if it's in the column space, the easiest thing to do is set up a linear system. So augment with the row you're interested in. Okay, we're going to row reduce that matrix. Okay, I've been kind of doing them off screen here, but I'll give you a shot here. Edit, so I'm going to have a 2 by 3. Okay, I'm going to type in my matrix, -2, 10, -2, 3, -15, and 3. Okay, we're going to row reduce that. I get 1, -5, 1 across the top. Okay, 1, -5, 1 across the top here, and all zeros along the bottom row. Okay, so this is a consistent system. So this means that B is an element of the column space of A, okay, because the system is consistent. Okay. So the question would be then, I need AX equal B to be true. So what value of X will accomplish this? Okay. Well, I've solved the system here. I have that x1 is equal to 5x2 plus 1, and x2 is a free variable. So the x vector that would solve this system, pick a value for x2. How about 1? That's nice and easy. 5 times 1 plus 1 would get us 6. So if I take my matrix A, multiply it by 6, 1, I get the output -2, 3. Okay. Now for the null space, so that was the column space. Now if I go to the null space, I want to know if AX equals 0. Well, the easiest way to find that out is to simply just do that multiplication. Okay, so I got my matrix A. I've got my vector B here, -2, 3. I really should put B here and not X. Okay. And I want to multiply them. Okay, so I'm going to do -2 times -2 is 4, plus 30. Okay, so I get 34. I'll go ahead and do the bottom one, even though we don't need to. -2 times 3 is -6. And then -45. So -6 and -45 is a -51. The important thing, though, is that this is not the 0 vector. In order to be in the null space, it would have to multiply to be the 0 vector. Now, that does not mean that all vectors have to be in one column space or null space. All 4 things are possibilities. A vector could be in the column space only, the null space only, it could be in both, or it could be in neither. But you find the column space find if a vector is in the column space by doing the augmented matrix, solving the system. You can figure out what vector X will do it. You can find if a vector is in the null space by multiplying. Okay. If you know a basis for the column space and null space, you can also compare your vector to those bases and figure out if they're a linear combination. Okay. But if you don't have a scaffolded problem where maybe you've already found this information, if you've already found this information, use it to your advantage. But if you haven't found this information, you don't have to find it if you're just looking at some specific vector v. Okay, null space, you do the augmented matrix and row reduce. Column space, you simply multiply and see if you get 0. Okay. The last bit of terminology we need to introduce, and this actually is a new bit of terminology, it's really the only new bit in this section, but it's not too new, is the idea of a row space. Okay, so a row space. Sorry, let me get that camera cooperating with us here. There we go. So row space. Okay, so if I've got a matrix A, 2, -1, 1, 0, 1, 1, -2, 3, 0, and then we'll do a fourth row here of 1, -6, 1. Okay, my row space, much like my column space, corresponds to what happens in the rows. Okay, column space, right, was the columns, row space is the rows. Okay, so if I'm looking for a basis for that row space, the easiest thing to do is to take the transpose, because that will make my rows into my columns. So I got 2, -1, 1 going down. My second row is now my second column, 0, 1, 1. Third row is now the third column, and the fourth row is now the fourth column. Okay, so I just flipped it to A transpose, okay, and then row reduce this. Okay, we're going to go in here, we're going to put in our matrix. Okay, our matrix is 3 by 4. I've got 2, 0, -2, 1, -1, 1, 3, and -6, and then 1, 1, 0, 1. When I row reduce this, I get 1, 0, 0, 0, 1, 0, 0, 0, 1, and I get -5.5, 6.5, and -6. Okay, so I have 3 linearly independent columns of the transpose, which correspond to rows of the original. Okay, so a basis then for the row space, okay, so row A is equal to the span of these first 3 columns, which correspond to the first 3 rows. Okay, but we still think of them as vectors, so we still write them vertically. Okay, so we have that first column of the transpose, 0, 1, 1, second column, 0, 1, 1, and the third column, -2, 3, and 0. Okay, so the row space is just the same thing as the column space, but for the rows. So figure out what's independent. If you need an example of a vector in the row space, well, just take one of the rows and make it a column vector. Okay, if you need an example of one in the null space, find a reduced, example of one in the null space. Find using our previous example, find one that we reduced. We wrote that representation. Here's a vector in the null space. I could multiply it by 3 if you wanted to, so I'd get 1, 3. That would also be a vector in the null space. Okay, you need an example in the column space. Take one of the columns from the original matrix. Okay, remember that the 0 vector is in all of these spaces because these are subspaces. Okay, they're all subspaces, assuming you have a setup that makes sense. They're all subspaces, so 0 is an element of any of these. Okay, kind of abusing notation, but any, right, column space, null space. Let me just write them all separately. Col A, null A, or row A, any of the above. Okay, row space doesn't have as much utility because really we're just talking about the column space of the transpose, but we do use it occasionally. Okay, and the other terminology there is, right, the kernel is the same thing as the null space, just for a linear transformation, and the column space is the same thing as the range, just for a linear transformation. Okay. All right, so that concludes section 4.2. Okay. Again, that's a lot of overlap with some previous things we've done. Did you get the idea? And 4.3 then is also going to be a bit of an overlap where we talk about linear independence and bases. Okay, linear independence and bases. So chapter 4, we repeat several of the things we've done before, just looking through the lens of a vector space now, kind of giving them a different title and a different flair. Okay. When we get to chapters 5 and 6, we really do change topics a bit. Chapters 5 and 6 take a look at some different things that we haven't seen before, some new terminology when we get to those chapters. But we still have a few sections left in Chapter 4. 4.3 is up next, and I will talk to you during that video.